Okay, Assalamualaikum and a very good afternoon. So this 6.7 is the last subchapter from chapter 6, which is absolute maximum shear and moment. So previously from 6.1 to 6.6, we have seen how to draw an inference line for beam, for trusses and for floor girders. And then we have seen how to determine the maximum shear positive and the maximum moment positive along the beam or on the beam. And here in 6.7 we want to know, or we want to determine, both of the location of the point in the beam and the position of the loading on the beam together, so that we can obtain the absolute maximum shear and moment caused by the concentrated point loads. So here in this 6.7, we want to know where is the best location in the beam and what is the position of the point load, the best position of the point load to be placed on the beam, so that we can obtain maximum shear, absolute maximum shear. We can obtain absolute maximum shear and moment caused by the concentrated loads. Okay, for example, here we start with shear. So for cantilever beam, the absolute maximum shear will occur at a point just next to the fixed support. Here we can see it is a cantilever beam. So you have a concentrated loads, concentrated series of load, 3 concentrated series of load. And of course, when you want to calculate the support, here, the fixed supports, so we can know the reactions or the total fixed support here must be tally with the point load, the concentrated of point load. So from there we know that the maximum shear will definitely occur somewhere here. So this is the maximum shear. I mean, without calculation you can predict where is the best place to determine the maximum or the absolute maximum shear. And here, for a simply supported beam, you can also calculate. Let's say if you have one concentrated loads, second concentrated load, third concentrated loads, you have a series of 3 concentrated loads. If you want to determine where is the best place for absolute maximum shear, of course you can predict by the support reaction here, FAY, and here FBY. So of course you can have like this. So definitely you know this is the location for absolute maximum shear. Okay, now we want to see moment. How to determine the maximum moment for a cantilever beam occurs at a point where absolute maximum shear occurs. So for cantilever beam also it's quite simple. So you know, when you plot a moment for a cantilever beam, of course there will be a value here. So it would be like this, somewhere here. So you have moment value here, because this is cantilever beam and this is a fixed support. So for a fixed support, when you draw a moment, there will be a value here. So definitely you know this is the maximum absolute. This is the moment absolute, maximum moment absolute, or absolute moment maximum. Maximum moment, absolute maximum moment, at this point. Okay, but for a simply supported beam, when you has a series of concentrated loads, you can predict, but it's quite difficult. Yeah, that's why it's stated here. The for a simply supported beam, yeah, for a simply supported beam, the critical position of the loads and the associated absolute maximum moment cannot, in general, be determined by inspection. Yeah? So, for the case of series of maximum, for the case of series concentrated loads, yeah, of course you can predict also the maximum moment, but you don't know where is the exact place. Yeah, let's say you have three concentrated loads, F1, F2 and F3. So when you draw the moment, yeah, when you draw a moment, it's like a straight line. Yeah, so of course there will be a value here due to F1, and then another value here due to F2, and there may be another value here. Is a straight line. Sorry, it's a straight line due to F3, and then backs to 0. Yeah, so we don't know what is the exact location, provided that it doesn't give you the distance here. So in order to know where is the best maximum, the absolute maximum moment, here you need to find the resultant force first. Yeah, by doing this, and then you can determine the distance, then you know where is the exact place to get the absolute maximum moment. So in this textbook, they already come up with the formula. I mean, they do the cut-off section to the beam, and then they calculate the AY. I mean, based on the series of concentrated load, first of all, you need to find the support reactions, yeah, which is AY. Then from there, you can cut the beam, yeah, using cut-off section. Where is it? They didn't put here. If you have the textbook, you can go to page 274. Yeah. So you have page 274, and you can cut somewhere here. Yeah. So the beam is cut somewhere here, and you can find the moment here. Yeah. So based on this moment, yeah, do the submission moment at this cut section, then you can have M2 here. Yeah. This is the moment at cut section. So from there, you can determine what is the X. Yeah, meaning that the distance between the resultant force to the next point load. Yeah. So then we can conclude that the absolute maximum moment in a simply supported beam occurs under one of the concentrated forces. Yeah? So meaning that maximum always occur under one of the concentrated forces, such that this force is positioned on the beam so that it and the resultant force of the system are equidistant. So the force and the final one, the force and the resultant force, the force and the resultant force must be in the same distance from the beam center line. Yeah. So you can use this equation to calculate the distance between the resultant force and the next point load. Okay. So, and then, okay, so this absolute maximum shear moment diagram, I mean the formula here is only applicable for a simply supported beams and cantilever beams, yeah. But other than that, you need to use these envelopes of maximum influence line values, yeah. Okay, so we move to the first example in 6.7, the only example in this slide. So this one 6.21, page 276. Okay. Determine the absolute maximum moment in the simply supported bridge deck shown in this figure. So you can see from this car, the car carries three series of wheel concentrated loads, yeah, 8 kilonewton, 6 kilonewton and 4 kilonewton. So from these three series of point load, first of all you need to calculate what is the resultant force. Okay. So when the car moves to this bridge deck, you need to find the absolute maximum moment in this simply supported. Okay, what you need to do, the first step is to calculate the resultant force and then determine the distance, yeah, using the equation just now, or from this they do the submission at C, which means that because you don't know the resultant force, the distance of resultant force with the next point load, yeah. So in this case, they assume submission moment at C, yeah. From there, they will find the X bar is 2 meter. Okay. So from here 2 meter, then you know that this 2 meter is in same distance, between the final between the resultant force and the next point load. So in that case, they place the concentrated, the three series of concentrated loads on the beam. Yeah. So you can see here the distance is 2 meter from 8 kilonewton to FR, or the resultant force, and then the FR to the next point load, which is 6 kilonewton, must also 2 meter. Okay. So from there, you can calculate what is the AY and then cut the section, because here you assume that the maximum moment may be occurred under 6 kilonewton. Yeah. So you cut after immediately 6 kilonewton, then you have this diagram. So you find that the submission moment MS, yeah, the moment at S is 26.0 kilonewton. Okay. So now try to move this final resultant force after the center line, because here they put 2 meter between this, So now in this one, they try to arrange the center line happen to be in the middle between 8 and final resultant force. So again here must be in the same distance. So 2 meter, So means that here 1 meter and then here 1 meter. Okay. So from there, they cut the section. So just try and error. I mean, we don't know whether at 6 kilonewton may have the absolute shear absolute moment, or maybe at 8 kilonewton you may have absolute moment. So that's why they cut this immediately after 8 kilonewton. Then calculate the MS. So from there, they calculate the MS, or the moment, is only 24.5 kilonewton meter. So means that by comparison, if you place the center line between final resultant and 6 kilonewton, or center line between 8 kilonewton and 5 and FR, it shows that the first assumption or the first calculation give the highest moment. Yeah. So which occurs under, by comparison, the absolute maximum moment occurs under 6 kilonewton load when the loads are positioned on the beam as shown in figure 6.37b. So the answer would be this one. Yeah. Okay. So I think we're done with chapter 6, and before that, the concept quiz as usual. Yeah, just to see your understanding. What is the influence line? Yeah, I did mention in the beginning of the chapter 6, the influence line is a diagram, yeah, or the line to indicate the value of the reactions, yeah, shear or moment at a specific point on the member based on a unit load that move along the structure member. Yeah. So influence line is different with bending moment diagram. So this shows only at a point of the member. Yeah. But bending moment diagram shows the moment, or shear force diagram also shows the diagram along the member. Yeah? So that's the difference. Okay. So second one. Name 2 procedures to construct the influence line. Yeah. So if you still remember, in the beginning of the chapter 6, in 6.1, 6.2, yeah, there are 2 approach that you can construct the influence line, where the first approach is you can use tabulate value. The second approach is use the influence line equations. Okay. So there are 2 procedures. Using tabulate value means that you put a table, construct a table, move a unit load step by step, and then you calculate the influence line. The shear or the moment based on the what kind of influence line that you want to draw. Yeah. And then the third one, how to construct the influence line for girders and trusses. Okay. So again, the influence line for a beam, you move a unit load at each point. So same to this line for girders and trusses. Yeah. So to construct, a unit load is placed at each panel joint or each panel point. Yeah. So this is the method that you use to construct the influence line for girders. Yeah. Place the unit load at each panel. Yeah. This is applicable for girders, floor girders, and place a unit load at each joint. Yeah. So this is for truss. This is normally for girders. Okay. Okay, the last one. How to find the maximum shear or moment in the members due to a series of concentrated loads. Okay, so this is, you need to refer back subtopic 6.6, where you can try by trial and error. You calculate by trial and error. You move the concentrated loads at each location. So you try to calculate the diagram, construct the influence line first, and then calculate the value, multiply with the unit loads, multiply with the point loads, yeah. Or you can also use the equation 6.1, yeah. In 6.6 you can use the equation 6.1 or 6.2 and 6.3, yeah, to construct the maximum shear and moment based on the influence line diagram. You multiply with the jump, the distance, and so on, yeah. So refer back subtopic 6.6. Okay, so I think we have done for this, and we have completely seen chapter 1 until 12, yeah, with Dr. Catherine also. So okay, I wish you good luck for your final exam. Thank you.